Hi, my name is Jonathan Charles, and welcome to Cisco SD WAN architecture, OMP, or the Overlay Management Protocol. So what we're going to do in this section, we're going to talk about the OMP and what it actually does. This is going to be the protocol that runs on our overlay network. This is, remember, the fabric that we're running on top of our existing WAN environment. Okay? And in this section, what we're going to do is we're going to cover OMP. The whole point of all the components we talked about in the last section is to bring up the overlay network. And you can't talk about the overlay network without talking about the overlay management protocol. This is going to be at the heart of the overlay routing that allows us to build those dynamic, scalable, IPsec secure VPNs. This allows all of our vEdge devices to communicate directly over any type of network, MPLS, internet, point-to-point, Metro Ethernet, satellite, cellular, 2 tin cans, or anything else. If you can ping the other side, we can build a tunnel across it. So this is the routing protocol we're going to use, OMP, for establishing and maintaining the control plane and used for exchanging routing policy and management information between the vSmart controllers and our vEdge devices. It's enabled by default on all devices, vSmart and vEdge, and automatically will start initiating those OMP peering sessions between themselves and vSmart. The reason this scales so well is that we don't create a full mesh network of every vEdge to every other vEdge. The vEdges just make a few connections back to a handful of vSmart controllers. So, for instance, each vEdge is going to make a connection to its associated vSmarts, sending its traffic to each one. Its traffic that it knows about to each one, all of its routing prefixes. The vSmarts then communicate among each other and then distribute that information back down. The advantage of this is that we don't have to create a full mesh network like we would if we were creating a traditional IKE-based IPsec network, in which case each router would have to establish a control plane connection to every other router in the topology, resulting in quadratic n-squared control plane complexity that doesn't scale. So it's going to operate inside bidirectional certificate authenticated TLS connections established among the vSmart controllers and between the vSmart controllers and the vEdge routers. It allows the exchange of full reachability without reliance on traditional routing protocols, such as OSPF and BGP, over those IPsec tunnels. It also allows the assimilation and dissemination of centrally defined data and application-aware routing protocols. So we can configure a policy on vManage up in here, all right, distribute it to the vSmarts, and then the vSmarts will distribute them down to the vEdges. It also allows a high degree of scalability by dramatically lowering those control plane complexity, right? Because each device is actually only connected to 2 vSmarts, even if we have 10 vSmarts, we'll still only make a connection to 1 and a backup or 2. We're not going to make a connection to all 10. And we're definitely not going to make an individual mesh connection to all 200 or 300 vEdges in our network. In contrast, if we had a traditional IKE-based IPsec network, each router would have to establish a control plane connection to every other router. All right? And every time you changed a prefix at a site, you would have to go to every other site to change those crypto maps to match. And I don't want to do that, and neither do you. So the only component we're going to have here that has to have a public IP is the vBond. And to make sure that it has to be able to communicate with both the vSmart and all the vEdge devices, especially even if they're behind NAT. The purpose of the vBond is to authenticate the vSmart controller and the vEdge routers and coordinate their connectivity. Each vBond has a persistent control plane connection in the form of a DTLS tunnel, and each vSmart controller has a temporary DTLS connection to each vEdge when it comes online. They are then authenticated via that built-in certificate and then pointed to their vSmart controller. So the vEdge boots up, finds its vBond, then gets a list of vSmarts to connect to. Super easy, barely an inconvenience. All right. And this is a reminder that the vBond has to have a public IP. It has to be reachable via all devices. The vSmarts and the vEdges can be behind NAT. They'll register the vBond, and then vBond will make sure that we have connections back to them. Okay? So here's some terminology I want to let you know here. We're going to be talking about these statements and using them back and forth, and I want to make sure that as we're using them going forward, you're aware of them. Please note this down, because when I say VPN 0, I mean transport side. When I say VPN 512, I mean the management VPN, and VPN 1 through 511 are going to be for the service side. And what I mean by that is that's the inside of the site network. Those are the routes we're advertising into the overlay. The VPN 0 is our overlay network that we're running on top of our MPLS and internet connections. Okay? That transport side is always VPN 0. All of those connections, your MPLS, your internet connections, are all going to be inside VPN 0. It's always going to be tunneled and encrypted unless we use split tunneling, in which case we're going to route to the internet, but we'll get to that. All right? The service side, the side we're going to be using and we're running connected and static and OSPF and BGP routing from is going to be between VPN 1 and 511. All right? And then we can apply policies to each VPN, so you're going to want to break those out by prefix. Okay? So to have any-to-any communication among all routers are going to have to learn all prefixes, which is the default route distribution policy. Generally, vEdge devices will learn their server-side prefixes via the connected, static, and dynamic. All right. Just ERGP is not currently supported, but it might be by the time this video is released. All prefixes learned from the server side on a router are advertised to the centralized controller, the vSmarts that we talked about on the last couple of slides, which then reflects the information to other routers over the network's control plane. The controllers do not handle any of the data traffic. They are only involved in control plane communication. Each vSmart's job is only to tell the vEdges about which vEdge, other vEdge holds which prefixes and which ones to go, how to get to the other side. Okay? No traffic is ever sent to the vSmarts. All right? And just to remember, I want to make sure we mention this. VPN, the transport side is always going to be VPN 0, and it's always going to be the overlay side, and VPN 512 is going to be used for management. You'll see how we configure that later. And VPNs 1 through 511 are where we're going to configure our connection to the inside of our networks. Okay? So some other terminology here. The TLOC, that's our transport locators. This identifies all the transport locations in the overlay network that connect to physical transport, such as the point at which a WAN interface connects to a carrier. All right? A TLOC is going to be denoted by a 3-tuple that consists of a system IP address, an OMP speaker, a color, and an encapsulation type. All right? And the OMP is going to advertise each of these separately. So each service-side route advertised into OMP is advertised with the above properties. Now, we don't use an IP address or an interface IP address to denote a TLOC. IP addresses move, change, and get DHCP and other things. We don't want them to do that. So we're going to use a system IP address to identify a TLOC, and that ensures that a transport endpoint can always be identified, regardless of what IP address is currently the highest on the device. Just so you know, this IP address, it's a non-routable identifier, so it's not actually an IP address. It's a 32-bit dotted decimal, so it looks like an IP address. So if you see it as an IP address and you see like 1.1.1.3, all right, that doesn't mean that that's the IP address of it. That's just the identifier for that tunnel. Okay. We also use a color to indicate what type of WAN interface on the vEdge router that we're going to be using. All right. So if we want to use MPLS, we'll label that as an MPLS color, for instance. There's a bunch of predefined colors built into the system, which are assigned in the configuration of those interfaces. Okay. And just as an example of some of the colors that we have here, we have 3G, Biz Internet, blue, bronze, custom, green, etc. Okay? You can add additional colors, but what we use the colors for is to determine whether we're private or public. And the encapsulation, of course, is going to be the tunnel interface, what we're going to use on the tunnel. It's going to be either IPsec or GRE, but it's going to be IPsec most of the time. Okay? And again, we talked about that system IP. It's just a unique identifier. But basically, when I tell you that this prefix is available on a vEdge device, I'm going to tell you what node ID we're going to be sending that traffic to. That node ID is going to be the device, the vEdge that's hosting that prefix. Okay? It's just used internally on devices loop, basically as a sort of like the device's loopback address in the transport VPN. VPN 0. Remember, transport VPN is always your VPN 0. It's a fixed system address. It's not a real IP. And by the way, it's not the same as a loopback. I just said it was a loopback, but it's not the same as a loopback because it's not a routable IP. Okay? Generally, what we're going to do is we're going to take a site ID and turn it into an IP address. So for site 1, we would assign 1.1.1.1 to it. And if we had 2 devices there, the second device would be 1.1.1.2, right? So that way we can define it with a site ID and some way that I can easily recognize that site ID as belonging to it. So basically, we're going to use this as we use the system IP as the router ID for BGP or OSPF. If you configure a router ID separately, which I recommend that you always do, then that router ID will trump the virtual IP address. The organization name is case sensitive, and it must be identical to every device on your network. It has to match the name of the certificates, and if it doesn't, the device will not come up. And the site ID is going to be a numeric identifier of the site in the Cisco overlay network. It must be the same for all Cisco SD WAN devices that reside on the same site. So if you have 3 SD WAN devices in a virtual environment, a VRRP or something else where they're connecting at the same location, you need to make sure that they have the same site ID so that we can route traffic correctly. Okay. So the transport locators, and we talked about these a moment ago. Basically, we talked about how they're defined. These are basically going to identify the physical interface where a vEdge router connects to the WAN transport network or to a NAT gateway. It's identified by a number of properties, the primary of which is that IP address color pair, which can be written in a tuple, IP address color. In this tuple, the IP address is the system IP. The color is a fixed text string that identifies the VPN or traffic flow within a VPN. And OMP advertises TLOCs using TLOC routes. So if I get a prefix from you, let's say your vEdge sends me a prefix of 192.168.1.0/24, I'm going to advertise it to everyone else using your system ID and color so that everybody else gets it, knowing whether or not their color should be talking to your color. And you can, by the way, the color is used for determining whether or not you want like colors to talk to each other or not. There's an option whether or not we can restrict that. The default is not to restrict that, and we'll create tunnels between all sites. Remember, if there's IP connectivity between 2 sites, we're going to create connections over all of the available tunnels. Okay? And remember, we advertise these up to TLOCs, these TLOCs to the vSmart, and then the vSmart sends them back down to all the vEdges. Okay? All right. By the way, just to give you an idea, there's that full mesh environment that we would have had to create manually if we didn't have the vSmarts managing all the vEdge connectivity. This is a much simpler way to do it. Basically, all we have to do is create those edge connections, put all those edge connections into the network into VPN 0, and then the vSmarts will create that full mesh connectivity for us without us having to do it ourselves. So we've talked about colors a couple of times. Let me go into them in a little more detail. We're going to get into them further as we go and we create more. We actually get into the configuration of this and we show you how we're actually doing it. But the specific color is used as categorized as private or public. So the private color is MPLS, private, et cetera, and all the other colors are going to be public. It's very important and has implications on vEdge to vEdge and vEdge to controller communication. By default, we're going to try to build TLOCs between all VPN 0 interfaces regardless of color. If we choose, we can restrict an interface to only build tunnels with the same color. So like, for example, if you have an MPLS color and those devices are only connected to other MPLS devices because you have no internet access there, you don't want that MPLS color to try to make tunnel connections to internet colors and other public colors that it's not going to be able to anyway. So then we have a bunch of private colors, Metro Ethernet, MPLS, private, etc. And they're going to use private addresses to connect to the remote site, a vEdge router in a private network. You can use these colors in a public network if there is no NAT device between the local and remote vEdge routers. For example, if you have an MPLS network, we won't try to form TLOCs to internet interfaces. Okay? Restricting those WAN transport tunnels by color allows our local WAN transport tunnels to be created and a bidirectional forwarding session for the tunnel to be established to the remote vEdge router only if a tunnel of the same color exists in the remote router. So if I've got one site that has an MPLS connection and another site that doesn't, I'm not going to try to build a tunnel between my MPLS session and to an internet site that doesn't have MPLS on it. Okay? It reduces the additional traffic being created and avoids creating connectivity where none exists. Okay? So the Cisco SD WAN builds a secure IP fabric that includes the following elements. Routing and the routing advertisements to establish and maintain the flow of traffic through the network. Layer 3 segmentation using virtual routing and forwarding to isolate various flows of traffic using those VPN numbers. Authentication and encryption, policies for routing and data traffic, and identifies all those transport side links and automatically encrypts traffic between sites. It has several benefits. The Cisco SD WAN fabric itself authenticates all devices participating in the network, and the fabric automatically exchanges encryption keys associated with the transport links, eliminating the need to configure thousands of pairwise keys. The fabric ensures that the network is not prone to attacks from the transport side because it's all encrypted. And I'd like to mention this again because it's going to come up over and over and over again. VPN 0, as we can see here, VPN 0, which is connecting the transport side, and then VPN 1 and 2 that we see on the A, B, C, and D subnets, those are our local user traffic, our so-called service side. That's where we're going to run our BGP, OSPF, and bring in our connected interfaces or any static routes into the environment. And then VPN 512 is how we connect back to vSmart and get our OMP updates. So the OMP is going to be that central component of that SD-WAN fabric. And it's TCP based and it's highly extensible. And it's that control, that glue that holds the entire SD-WAN fabric together. It's how the vEdge devices are going to learn about the prefixes that are advertised by all the other vEdge devices. And remember, those vEdge devices do not communicate from a control plane perspective to each other. They only pass data between each other. The control plane traffic is between the vEdge devices and the vSmarts using that overlay management protocol. All right? And that's the end of this section, the end of OMP. So that what we've covered in this section, we've talked about what SD-WAN is, that it's software-defined wide area networking. Basically, we're going to run an overlay protocol on top of the underlay protocol. That underlay protocol is going to be your existing MPLS and internet circuits. The overlay protocol is OMP, which is going to establish and make sure the routing is up, and then we have secure connections between each sites over your existing WAN network. And remember, we can run that over any transport circuit. If we have IP connectivity, we can run OMP over it. Thank you for watching, and this concludes this section.